Between galaxies lies a darkness so vast that light may travel for millions of years without reaching another world. Yet, this apparent emptiness is not truly empty. Hidden within distant gas, ancient stars, rocky planets, and even the atoms of the human body are neutrons. Silent particles that help build nearly everything around us. This journey crosses the greatest distances in the universe before entering the deepest layers of matter itself. If you enjoy calm science documentaries, please like the video, subscribe to the channel, and begin the journey into intergalactic space. At the greatest observable scale, the universe appears as a vast sphere centered on every observer, not because any place holds a special central position, but because light reaches each location from all directions. The outer boundary of this sphere is called the observable cosmic horizon. It marks the greatest distance from which information carried by light has had time to arrive since the early universe became transparent enough for radiation to travel freely. This boundary is not a wall surface or material edge. It is a limit created by time, distance, and the continuing expansion of space. The age of the universe is about 13.8 billion years, yet the most distant regions that can be observed today are much farther away than 13.8 billion light years. This apparent difference comes from cosmic expansion. While ancient light travels towards the Milky Way, the space between its source and its destination continues to stretch. A galaxy that releases light in the distant past may now stand tens of billions of light years away. In present-day distance, the radius of the observable universe is therefore estimated at about 46 billion light years, giving the visible region a diameter of roughly 93 billion light years. This enormous scale does not mean that light moves faster than its known limit. Light always travels locally through space at the same constant speed in a vacuum. The growing distance develops because space itself expands between widely separated regions. General relativity describes this expansion as a change in the geometry of the universe rather than ordinary motion through a fixed background. Galaxies separated by enough distance can recede from one another at an effective rate greater than the speed of light without violating the local rule governing light. Their separation grows because the intervening space stretches. The observable horizon depends on the history of that stretching. Expansion is not constant in the simple sense of proceeding at one unchanged rate. In the early universe, radiation and matter influence the expansion strongly. Later, remains important, while large structures form through gravity. In the more recent cosmic era, observations indicate that expansion accelerates. The cause is described by the term dark energy, a name for the unknown component associated with this acceleration. Measurements strongly support its overall effect, while its physical nature remains uncertain. As expansion continues, light from some extremely distant regions may never reach the Milky Way, even across unlimited future time. Those regions can already exist within the larger universe, but their signals remain outside causal contact. A causal connection exists when information or influence can pass between locations without exceeding the local speed of light. The cosmic horizon therefore separates what can in principle be observed from what remains inaccessible. It does not define the total size of the universe. The whole universe may extend far beyond the observable region, and current evidence does not establish whether its full size is finite or infinite. On the largest measured scales, the universe appears nearly uniform. Galaxies gather into clusters, filaments, walls, and broad empty regions, yet these patterns become statistically even when averaged across sufficiently large distances. This property is called homogeneity. The universe also appears broadly similar in every direction, a property called isotropy. Together, these observations support cosmological models in which no preferred direction or central location exists on the greatest scales. Every distant observer sees an observable sphere centered on the observer's own position. The horizon also changes with time. As the universe ages, light from more distant events can complete its journey, allowing new regions to enter the observable domain. At the same time, accelerated expansion affects which distant sources remain visible in the far future. Light already traveling from some galaxies continues to arrive, but later signals emitted by those same galaxies may never cross the growing separation. Their observed light becomes increasingly red-shifted, meaning that cosmic expansion stretches its wavelength toward longer, lower energy forms. Over immense periods, such galaxies grow fainter and appear to slow near an observational boundary. Redshift provides one of the main ways to describe cosmic distance. It does not usually give a simple present-day distance without a cosmological model because the relationship depends on how expansion changes through time. Astronomers combine redshift measurements with observations of standard candles, standard rulers, galaxy clustering, and background radiation. These methods help reconstruct the expansion history and estimate distances across the observable universe. The resulting picture is precise in broad structure, although measured values such as the present expansion rate still shows some disagreement between different methods. The horizon is therefore both a physical limit and an observational concept. It expresses the maximum reach of evidence available through electromagnetic radiation and other signals that move at or below light speed. Neutrinos and gravitational waves also carry information across cosmic distances, but they obey the same causal structure. Their usefulness differs because they interact with matter in different ways. Yet none provides access beyond the fundamental horizon defined by space-time history. Near this outermost scale, individual galaxies no longer dominate the description. The main features are expansion curvature time and the distribution of matter and energy across immense volumes. Current measurements indicate that large-scale spatial curvature is very close to flat, meaning that the geometry of space follows ordinary Euclidean behavior across broad scales within observational precision. A flat observable region can still belong to a universe that is vastly larger than what can be seen. Small departures from flatness may remain below present detection limits. The observable cosmic horizon surrounds all known structure without enclosing it like a shell. It moves with cosmic history, shaped by the finite age of the universe and by the changing rate of expansion. Beyond it, no direct image arrives, no spectrum can be measured, and no signal can confirm local conditions. Scientific models can describe possibilities consistent with known physics, but observation cannot currently test those distant regions directly. At the outer limit, knowledge rests on the light that reaches the present, carrying a record of a universe whose most distant visible parts are seen not as they are now, but as they existed in an ancient cosmic past. This horizon remains the quiet boundary of measurement where finite travel time and expanding space together determine the deepest accessible reach of cosmic history. Beyond the broad boundary of the observable universe lies the oldest light that can still be detected directly, a faint field of microwave radiation spread across the entire sky. This radiation is called the cosmic microwave background. It does not come from a single star galaxy or explosion. It fills space almost uniformly and carries a record of the universe at a time when matter and light first become able to travel separately across great distances. In the earliest stages of cosmic history, the universe is far hotter, denser, and more compact than it is today. Matter exists mainly as a glowing plasma, a state in which electrons move freely among atomic nuclei. Photons, the particles of light, cannot travel far through this environment. They scatter repeatedly from the free electrons, much as light scatters through a dense fog. The young universe is therefore opaque, even though it contains enormous amounts of radiation. As expansion continues, the temperature steadily falls. After about 380,000 years, the universe cools enough for electrons to join with nuclei, mainly protons, forming neutral hydrogen atoms. This transition is called recombination, although it is the first stable combination of these particles rather than a return to an earlier state. With far fewer free electrons available to scatter photons, space becomes transparent. Light begins to move freely across the growing universe. The photons released from this period continue traveling through space for more than 13 billion years. Cosmic expansion stretches their wavelengths during the journey. Radiation that begins largely as visible and infrared light becomes shifted into the microwave region of the electromagnetic spectrum. By the time it reaches present-day instruments, it has a temperature of about 2.7 degrees above absolute zero. This low temperature reflects the immense expansion that occurs after the light first travels freely. The cosmic microwave background does not mark the beginning of the universe. It marks the earliest moment from which ordinary light can move without being trapped by dense plasma. Events before this time remain hidden from direct electromagnetic observation because photons repeatedly scatter and lose information about their original paths. The microwave background, therefore, acts like a luminous surface surrounding every observer, though it is not a physical shell fixed in one place. It is a distant layer in time, seen wherever a line of sight reaches far enough into the past. Across most of the sky, the microwave background is remarkably even. Its temperature varies by only tiny fractions of a degree. This smoothness shows that the early universe is already highly uniform on large scales. Yet the radiation is not perfectly featureless. Extremely small temperature differences appear from place to place. These variations preserve traces of slight differences in density present in the ancient plasma. Regions with a little more matter produce slightly different patterns in the radiation than regions with a little less. Gravity gradually amplifies these small differences over billions of years. Denser areas attract more matter, while less dense areas become increasingly empty. The patterns in the microwave background, therefore, provide evidence for the early conditions from which later cosmic structure develops. They do not show mature galaxies or stars. They show the subtle, starting variations from which large concentrations of matter eventually emerge. Sound waves also move through the early plasma before recombination. These waves arise from a balance between gravity, which draws matter inward, and radiation pressure, which pushes outward. Their motion leaves a series of characteristic patterns in the microwave background. Astronomers study the sizes and strengths of these patterns to estimate the composition, age geometry, and expansion history of the universe. Observations from instruments on the ground, carried by balloons and placed in space, have mapped this radiation with increasing precision. Missions such as NASA's Cosmic Background Explorer, NASA's Wilkinson Microwave Anisotropy Probe, and ESA's Planck Observatory measure its temperature and polarization across the sky. Polarization describes the preferred orientation of the radiation's electric field. It contains additional information about conditions in the ancient plasma and about later interactions between radiation and matter. These measurements support a universe dominated by dark energy and dark matter, with ordinary matter forming only a smaller share of the total cosmic content. Dark matter does not emit or absorb a light in the ordinary way, but its gravitational influence affects the patterns seen in the background radiation. Ordinary matter includes the atoms that form stars, planets, gas dust, and living systems. The measured proportions fit a broad cosmological model with high precision, although several details remain under active study. One area of uncertainty concerns the earliest fraction of cosmic time. Some models propose a brief period of extremely rapid expansion called inflation. Inflation can explain the large-scale smoothness of the microwave background and the origin of its small density variations. Observations are consistent with many inflationary models, but they do not yet identify a single confirmed mechanism. Scientists continue searching for distinctive patterns in polarization that could reveal gravitational waves produced during that early phase. The microwave background also carries signs of everything it encounters after leaving the ancient plasma. Hot gas in galaxy clusters can slightly alter its energy. Gravitational fields bend its path through a process called gravitational lensing. Later generations of stars ionize gas between galaxies, changing the radiation's polarization. Researchers separate these effects carefully to recover the older signal, while also learning from the changes added during its long journey. Even with advanced instruments, the cosmic microwave background remains faint. Its radiation is mixed with signals from the Milky Way, distant galaxies, interstellar dust, and human technology. Careful observation at many frequencies allows scientists to distinguish the ancient background from these nearer sources. The resulting maps reveal a quiet field of radiation that reaches Earth from every direction, nearly uniform yet filled with delicate structure. At this great distance in time, the universe appears simple compared with its later complexity. Matter is spread smoothly. Atoms are newly formed, and free-traveling light carries the imprint of a young cosmos. The cosmic microwave background remains the oldest electromagnetic message available to astronomy today, preserving a record of conditions soon after transparency begins. Its faint glow defines the deepest, directly visible layer of cosmic history, where ancient radiation still arrives after crossing the expanding universe for almost its entire age. The earliest visible galaxies appear as faint concentrations of light scattered across nearly empty fields. Their light begins traveling when the universe is young, long before spiral and elliptical systems become common. These distant galaxies are observed through space telescopes and large ground-based instruments that collect weak signals stretched across immense distances. Each detection represents an ancient stage of galactic development preserved in light that has crossed expanding space for more than 13 billion years. Because light takes time to travel, observing a distant galaxy also means observing the past. A galaxy seen billions of light years away is not viewed as it exists today. It appears as it was when the light leaves it. The most remote confirmed galaxies are therefore seen during the first few 100 million years after the beginning of cosmic expansion. Their present condition cannot be observed directly, and their later history must be inferred from models and comparisons with younger galaxies at smaller distances. These early systems are compact, irregular, and active. They do not yet display the organized forms seen in many nearby galaxies. Their shapes often appear clumpy because star formation is concentrated in dense regions. Gas falls inward, gathers under gravity, and cools enough to form new stars. Interactions between systems disturb their structure. Mergers are common because many early galaxies grow by joining with neighboring collections of gas stars and dark matter. Dark matter provides the gravitational framework in which these galaxies develop. It does not produce light, but it forms dense regions that attract ordinary matter. Hydrogen and helium gas collect inside these dark matter concentrations called halos. As the gas becomes denser, parts of it cool and collapse. Stars form in groups releasing radiation that begins to transform the surrounding environment. The details remain under study because early galaxies are difficult to observe and several physical effects operate together. The stars within these young galaxies are not all identical. Some may belong to early generations formed from gas containing no elements heavier than helium. Such stars are expected to differ from later stars because their material lacks carbon, oxygen, silicon, iron, and other elements. The first generation, called Population 3 stars, has not been directly confirmed. Models indicate that many may be massive and short-lived, but their typical masses and formation patterns remain uncertain. Later generations form from gas enriched by earlier stars. When stars end their lives, they return elements to surrounding space through winds and explosive events. This chemical enrichment changes how gas cools and fragments. It allows stars with a wider range of masses to form. Early galaxies become places where the first cycles of stellar birth element production and recycling begin to shape matter into more complex forms. Astronomers identify distant galaxies largely through redshift. As the universe expands, the wavelength of light becomes stretched. Ultraviolet light emitted by young stars can arrive at detectors as infrared radiation. The greater the redshift, the earlier the observed stage of cosmic history. Instruments designed for infrared astronomy are important because they detect this stretched light more effectively than telescopes limited to visible wavelengths. A reduction in brightness at certain wavelengths also helps reveal distance. Neutral hydrogen absorbs light with energies above a threshold. In a distant galaxy, cosmic expansion moves this absorption feature toward longer wavelengths. Astronomers compare brightness through several filters and search for objects that disappear in shorter wavelength images while remaining visible in longer wavelength ones. Spectroscopy then separates light into its component wavelengths, allowing precise redshift measurements when the signal is strong enough. Gravitational lensing sometimes increases the visibility of these remote galaxies. A massive galaxy cluster positioned between Earth and a distant source bends space-time and alters the path of the background light. The cluster can magnify the distant image, making a galaxy bright enough to study. The image may appear stretched into an arc or divided into several copies. Scientists model the foreground mass carefully because the apparent brightness and shape depend on the lensing effect. Even with magnification, measurements remain difficult. Early galaxies are faint, small, and sometimes represented by only a limited number of detected light points. Dust can absorb ultraviolet radiation and re-emit energy at longer wavelengths. Gas around the galaxy can block part of the signal. Instrument noise and foreground objects can imitate distant candidates. For this reason, the status of the most remote galaxies changes as observations improve and additional spectra become available. Confirmed observations indicate that galaxy formation begins quickly on cosmic timescales. Significant collections of stars exist within several 100 million years of the early hot phase. Some detected systems appear unexpectedly bright or massive for their observed age. This does not necessarily conflict with established cosmology, but it requires careful evaluation of stellar masses, star formation rates, dust lensing, and possible active galactic nuclei. An active galactic nucleus is a compact, luminous region powered by matter falling toward a central black hole. The size and mass of early galaxies vary widely. Many contain far fewer stars than the Milky Way and occupy regions only a small fraction of its diameter. Others may already hold substantial stellar populations. Their star formation can be intense relative to their size, producing large amounts of ultraviolet radiation. This radiation escapes unevenly because surrounding gas absorbs some of it. The fraction that escapes is important for understanding how galaxies influence the intergalactic environment during this ancient period. Images of these systems often show only the brightest star-forming regions. Fainter outer material may remain below detection limits, so measured sizes can underestimate their full extent. Spectra reveal information about gas motion, chemical composition, and stellar populations, but interpretations depend on models. Different combinations of age, dust, and metallicity can produce similar colors. Metallicity is the astronomical term for the abundance of elements heavier than hydrogen and helium. At these extreme distances, every observation combines direct evidence with careful inference. Light records the energy produced by stars and gas, while gravity shapes the unseen framework around them. The earliest visible galaxies are not finished structures. They are changing systems assembled from smaller parts, forming stars rapidly enriching their gas and responding to the surrounding distribution of matter. Their faint images preserve the first observable stages of galactic organization, when scattered material gathers into enduring islands of stars within the young expanding universe. Deep cosmic galaxy fields reveal the universe not as a smooth darkness, but as a layered record of countless galaxies seen at different stages of development. These fields are created by directing powerful telescopes towards small regions of sky that appear nearly empty to ordinary observation. Long exposures collect faint light over many hours or days, allowing distant galaxies to emerge from the background. The resulting images contain systems separated by enormous distances yet compressed into a single, narrow line of sight. Each field covers only a tiny part of the sky. Even so, thousands of galaxies may appear within it. Some are relatively nearby and show clear spiral arms, bright central regions, or broad elliptical shapes. Others are much farther away and appear as small red points, Faint smudges or irregular fragments, their light reaches the telescope after traveling for different lengths of time. So one image combines many periods of cosmic history. The field becomes a visual sequence of galactic growth, although every object occupies its own distance and age. The apparent size of a galaxy does not alone reveal how far away it is. A small image may represent a physically small nearby system or a much larger galaxy at extreme distance. Brightness also depends on the number of stars, the rate of star formation, the amount of dust, and the wavelength being observed. Astronomers therefore combine images taken through many filters. Each filter records a selected range of wavelengths, helping researchers estimate redshift, stellar age dust content, and chemical composition. Deep fields often begin with visible light observations, but infrared measurements are essential for the most distant galaxies. Cosmic expansion stretches their ultraviolet and visible radiation into longer wavelengths. Near-infrared instruments detect light from early stars, while mid-infrared observations can trace warmer dust and older stellar populations. X-ray observations reveal energetic sources such as matter falling toward black holes. Radio observations detect cold gas, magnetic activity, and star formation hidden by dust. Together, these measurements turn a flat image into a more complete physical map. The deepest surveys are limited by sensitivity and resolution. Sensitivity describes the faintest light an instrument can detect. Resolution describes how closely separated objects can be distinguished. Increasing exposure time improves sensitivity, but background radiation and detector noise eventually limit the result. Larger telescope mirrors collect more light and usually produce sharper images. Space telescopes avoid the blurring and absorption caused by Earth's atmosphere, while large ground-based observatories contribute wide fields, spectroscopy, and observations at wavelengths accessible from the surface. Selection effects shape every deep field. A survey detects objects that are bright enough in the chosen wavelengths, while dimmer or heavily obscured systems may remain invisible. Galaxies with active star formation often appear more easily because young, massive stars emit strongly in ultraviolet light. Quieter galaxies containing older stars can be harder to identify at great distance. Dusty galaxies may disappear from visible images while remaining bright in infrared or radio observations. The observed population is therefore not a complete sample of every galaxy that exists in the surveyed volume. Astronomers use statistical corrections to estimate what is missing. They insert artificial galaxies into real images and test whether detection methods recover them. They model how brightness changes with distance and how surface brightness becomes more difficult to measure as redshift increases. Surface brightness is the amount of light received from a given apparent area. Cosmic expansion causes distant extended objects to fade strongly in surface brightness, making their outer regions especially difficult to detect. Deep fields help measure how the galaxy population changes over time. Researchers count galaxies of different brightness, color, mass, and shape. They estimate how quickly stars form within them and how much stellar mass already exists at each epoch. Results show that the overall rate of star formation rises during early cosmic history, reaches a broad maximum several billion years after the beginning, and later declines. Individual galaxies follow many different paths, so the field contains active systems, fading systems, merging pairs, and objects already dominated by older stars. Morphology. The study of form and structure changes across the field. Nearby galaxies often show settled disks, bars, spiral patterns, or smooth elliptical shapes. More distant galaxies are commonly smaller and less regular. Clumps of star formation can dominate their appearance. Frequent interactions stretch material, disturb disks, and create asymmetry. Some compact galaxies may grow from the inside outward, while others gain mass through repeated mergers. Observations indicate several growth pathways rather than a single universal sequence. Deep fields also reveal central black hole activity. Some galaxies contain luminous nuclei powered by gas falling into massive black holes. These sources can outshine the surrounding stars and remain visible across great distances. Their radiation affects nearby gas, while outflows can move energy and matter through the host galaxy. The connection between black hole growth and galaxy development is supported by many observations, though the detailed timing and strength of this relationship vary among systems. Cosmic variance introduces another limitation. Galaxies are not distributed perfectly evenly, so a small field may contain more or fewer objects than the cosmic average. One line of sight can pass through a dense concentration while another crosses a relatively sparse region. Astronomers reduce this uncertainty by observing several independent fields and by combining narrow, deep surveys with wider, shallower ones. The final images require extensive processing. Detectors record light along with noise, cosmic ray impacts, instrumental patterns, and small changes in telescope position. Multiple exposures are aligned and combined. Foreground glow is removed carefully, and colors are assigned to measured wavelength ranges. These colors may approximate human vision for nearby objects, but distant infrared data often require representative color mapping. The image remains scientific data rather than a direct view through an ordinary eye. Within a deep cosmic field, every faint shape carries a separate history. Some light begins its journey when galaxies are young, while other light leaves systems much later. The telescope gathers these signals at one present moment, placing ancient and recent structures side by side. The field, therefore, shows depth through time as well as through space. It reveals a universe filled with galaxies at many distances, each observed during one stage of its changing existence, and together they form a quiet, remarkably detailed, densely layered record of cosmic development. Vast, Cosmic voids occupy much of the large-scale universe, spreading between the brighter filaments walls and clusters where galaxies gather. They are not perfectly empty regions, but their matter density is far lower than the cosmic average. A void may extend across tens or even hundreds of millions of light years, containing only a sparse population of faint galaxies and thin gas. From a distance, these regions appear dark because they hold few luminous systems, yet their emptiness has structure, history, and measurable physical effects. A cosmic void begins as a slight underdensity in the early distribution of matter. In such a region, gravity draws material less strongly than it does in nearby denser areas. Matter gradually moves towards surrounding concentrations, leaving the underdense region increasingly depleted. As the universe expands, the void grows in size and contrast. Its interior becomes less crowded while matter collects along its boundaries. This process does not create a sharp hollow with a hard edge. Density usually changes gradually from the interior towards surrounding sheets and filaments. The largest voids form part of the cosmic web. Their boundaries are traced by galaxies, groups, and thin structures of dark matter. Several smaller voids can merge as the separating matter drains away, producing broader, empty regions. Other voids remain divided by delicate internal filaments that contain a few galaxies. Their shapes are not simple spheres. Gravity expansion and the surrounding distribution of matter stretch them into irregular volumes with ridges, tunnels, and shallow density gradients. Dark matter dominates the mass budget within and around voids, just as it does elsewhere on large scales. Although the concentration is low, dark matter still forms weak halos in which small galaxies can develop. These halos tend to be less massive than those found in dense clusters. Their slow growth reflects the limited supply of surrounding material. Ordinary gas also remains present, but it is thin, cool, and difficult to detect. Some of it absorbs light from distant sources, allowing its presence to be inferred through spectroscopy. Galaxies inside voids are uncommon, but they are scientifically valuable. Many are small blue and actively forming stars. Their isolation reduces frequent interactions with massive neighbors, allowing internal processes to become easier to study. Gas can continue feeding star formation over long periods because the environment does not strip it away as strongly as a cluster would. Even so, void galaxies are not completely untouched. They may experience minor mergers, internal feedback, and slow flows of gas along faint local filaments. Not every galaxy in a void shares the same history. Some contain older stars and little current star formation. Others show irregular forms and abundant neutral hydrogen. Their metallicity can be low, meaning that their gas contains relatively few elements heavier than hydrogen and helium. This may indicate slow chemical evolution, although observations show considerable variation. The small number of known void galaxies makes broad conclusions difficult, and deeper surveys continue to reveal systems that were previously too faint to detect. Void interiors influence the motion of surrounding matter. Because they contain less mass, they exert less gravitational attraction than denser regions. Matter, therefore, moves away from their centers in a relative sense, flowing toward the walls and filaments around them. The void itself does not push material outward through a separate force. Instead, nearby over-dense regions pull more strongly, and cosmic expansion carries under-dense space apart more rapidly. This difference causes voids to expand faster than the average cosmic scale. Their rapid expansion makes cosmic voids useful for studying dark energy and the geometry of space. Astronomers compare void shapes and sizes across different distances. A void that is statistically round in its own rest frame can appear stretched or compressed if the assumed cosmological model uses an incorrect relationship between distance and redshift. Collections of voids, therefore, provide a test of cosmic expansion. Measurements remain challenging because void boundaries are irregular and galaxy samples are incomplete. Gravitational lensing offers another method. Matter bends the path of light, so underdense regions produce a weaker lensing effect than their surroundings. When many voids are combined, statistically, background galaxy images show a small but measurable pattern associated with missing mass. This signal helps estimate the density profile from the center to the edge. It also tests how well observed galaxies trace the underlying dark matter distribution. The cosmic microwave background can carry subtle marks from voids as well. Photons passing through a changing gravitational potential may gain or lose small amounts of energy. In an accelerating universe, a large underdensity can leave a faint temperature shift through the integrated Sachs-Wolf effect. Individual signals are extremely weak, so researchers often combine many void locations. Some reported measurements appear stronger than simple models predict, but uncertainties in void selection and foreground removal remain significant. Void statistics depend on how a void is defined. One method searches for empty spheres between galaxies. Another identifies connected under-dense regions in a reconstructed density field. Different surveys use different galaxy populations, depth limits, and algorithms. As a result, catalogues may assign different sizes or boundaries to the same broad region. Scientific comparisons require consistent definitions and careful treatment of observational bias. Nearby examples help make these enormous structures more concrete. The local void lies close to the local group and contains far fewer galaxies than surrounding regions. Its underdensity contributes to the motion of nearby galaxies relative to the broader cosmic web. Far larger, named voids, have also been mapped, though their exact dimensions depend on the chosen boundaries and survey data. These regions are not unusual exceptions. They are a dominant feature of the universe on very large scales. Inside a cosmic void, distances between bright galaxies are immense. Starlight is rare, and most matter remains invisible. The region still contains gravity, dark matter, thin gas-weak magnetic fields, and occasional galaxies, but everything is spread across a vast volume. Its apparent emptiness results from comparison with denser surroundings rather than complete absence. By tracing where matter is missing, cosmic voids reveal how gravity organizes the universe. Their expanding interiors preserve the quiet imprint of underdensity, while their edges gather the material that gradually defines the visible cosmic web. They are broad records of cosmic growth shaped slowly, as matter leaves sparse interiors and settles into denser surrounding structures. Cosmic walls and filaments form the framework. They stretch across hundreds of millions of light years, linking galaxy groups and clusters in long strands and sheets. Together they create the cosmic web, a pattern produced by gravity, acting on small differences in the early distribution of matter. The web is not a rigid structure suspended in space. It is an evolving arrangement of dark matter gas galaxies and galaxy clusters that continues to change as matter moves toward denser regions. Filaments begin where gravity gathers material along preferred directions. In the early universe, matter is nearly even, but slight density variations remain. Regions with a little more mass attract nearby material. Collapse does not occur equally in every direction. Matter may first contract along one direction to form a sheet, then along another direction to form a filament. Where several filaments meet, dense knots develop. These knots often become galaxy clusters, while the spaces between the strands expand into voids. Dark matter provides most of the mass in this structure. It does not shine, yet simulations show an interconnected network forms before matter settles into the same pattern. Gas falls into dark matter filaments. As it enters, it can be compressed and heated. Some gas cools and flows toward galaxies, supplying material for star formation. Other gas remains spread through the filament at temperatures reaching millions of degrees. This thin intergalactic gas is difficult to observe directly. Much of it emits only faint radiation because its density is extremely low. Astronomers search for absorption lines in the spectra of bright background objects. When light from a distant quasar passes through a filament, atoms and ions remove energy at specific wavelengths. These narrow features reveal the presence, temperature, motion, and chemical composition of otherwise invisible gas. X-ray and ultraviolet observations are especially useful for tracing hotter material. A large fraction of ordinary matter in the nearby universe is expected to exist in this warm, hot, intergalactic medium. The term describes gas heated by shocks as matter falls into filaments and cluster boundaries. Observations have identified parts of this reservoir, but measuring all of it remains difficult. The gas is too diffuse for easy imaging, and foreground material can hide weak signals. Evidence from absorption emission and statistical studies broadly supports the predicted distribution, while the exact amount in different temperature ranges remains uncertain. Galaxies inside filaments do not sit randomly. Their locations follow the underlying gravitational structure. Small galaxies may move along the strands toward larger groups and clusters. The direction of a galaxy's rotation can sometimes show a statistical relationship with the orientation of its filament. This alignment is not universal, and it depends on galaxy mass merger history and local conditions. Simulations suggest that gas and dark matter flows can influence angular momentum as galaxies grow. Filaments vary greatly in thickness and density. Some are narrow bridges joining two clusters. Others are broad complexes containing many groups and branching strands. Their boundaries are gradual rather than sharp. A galaxy near the center of a dense filament experiences a different environment from one near its edge. Gas supply interaction rates and gravitational tides all change across the structure. These differences can affect how quickly galaxies form stars and how their shapes evolve. Walls are wider, flatter concentrations of matter. They can extend across immense distances while remaining comparatively thin in one dimension. Galaxies appear distributed through these sheets, with filaments often running within them or along their intersections. Some maps reveal wall-like patterns because the survey slices through three-dimensional structure. The apparent shape depends partly on viewing geometry, so careful reconstruction is needed to distinguish a true wall from several nearby filaments projected together. Astronomers map the cosmic web by measuring galaxy positions and redshifts. A redshift survey records where a galaxy appears on the sky and estimates its distance along the line of sight. Millions of such measurements create three-dimensional maps. These maps show dense clusters, long filaments, broad walls, and empty voids. The observed pattern closely resembles structures produced in simulations based on expanding universe cosmology, dark matter, ordinary matter, and dark energy. Redshift maps contain distortions caused by galaxy motions. A galaxy falling toward a cluster has a velocity in addition to the motion associated with cosmic expansion. This extra movement changes its measured redshift and can stretch clusters along the line of sight in a map. On larger scales, coherent infall toward filaments and walls produces another pattern. Researchers modeled these effects because they contain information about gravity and the growth of structure. Weak gravitational lensing provides a more direct view of mass. Light from distant galaxies is slightly distorted as it passes through the gravitational fields of foreground matter. By averaging the shapes of many background galaxies, astronomers reconstruct broad maps of dark matter. These maps show that visible galaxies trace only part of the web. The underlying mass distribution is smoother and more extended, with dark matter connecting regions that may appear separated in ordinary images. The cosmic web also affects signals traveling across it. Radio waves can interact with ionized gas and magnetic fields. Fast radio bursts, brief pulses arriving from distant galaxies, may help measure the amount of matter along their paths. Gravitational lensing can magnify remote sources, while dense structures alter the travel paths of light. Every crossing records some property of the intervening material, though separating the contributions of individual regions requires large samples. Filaments and walls grow slowly over cosmic time. Gravity draws matter from voids and less dense, surroundings increasing contrast. Clusters at filament intersections become more massive through mergers and continuing infall. The largest structures do not collapse into single-bound objects because cosmic expansion and dark energy limit growth across very large scales. Some parts remain gravitationally connected, while others gradually separate in an accelerating universe. At this scale, the universe resembles a network rather than a random field of isolated galaxies. Bright systems mark the densest parts, but most of the framework consists of unseen dark matter and faint gas. The walls and filaments guide motion, supply galaxies with material, and connect clusters across distances. Their forms preserve the influence of early density variations enlarged by gravity over billions of years. Through these long strands and broad sheets, matter gathers into the enduring architecture of the observable cosmos. Supercluster realms occupy immense regions where many galaxy groups, clusters, filaments, and walls share a pattern of motion. They are among the largest named structures in the observable universe, extending across hundreds of millions of light years. A supercluster is not usually a single object held together in the same way as a galaxy or compact cluster. It is a concentration within the cosmic web shaped by gravity, but also influenced by the continuing expansion of space. The term supercluster describes a region containing several clusters and numerous smaller groups. These components are linked by filaments of dark matter and gas. Between them lie thinner bridges, sparse galaxy populations, and partial voids. The boundaries are difficult to define because matter density changes gradually. Different surveys and methods may assign different edges to the same broad structure. A supercluster, therefore, has no simple surface, and its measured size depends on how galaxies' velocities and mass are mapped. Galaxies within these regions move under several influences. They take part in cosmic expansion, yet they also fall toward nearby concentrations of mass. A group may drift toward a cluster, while several clusters move within a gravitational landscape. Astronomers study these motions through redshift and distance measurements. Redshift alone includes both expansion and local velocity, so independent distance indicators are needed to separate the two effects. The resulting pattern reveals broad flows across tens or hundreds of millions of light years. One region is the Laniakea supercluster, which includes the local group and the Milky Way. Its name refers to a wide domain of galaxies whose measured motions tend toward a gravitational region called the Great Attractor. Laniakea spans roughly 500 million light-years and contains many groups and clusters. Its boundaries are defined by the directions of galaxy flows rather than by a sharp concentration of visible matter. Other classification methods place some of the same galaxies within differently named structures. The Great Attractor is not a single giant object. It is a region where several concentrations of mass contribute to a gravitational pull. Part of it lies behind the plane of the Milky Way, where dust and stars obscure visible observations. Infrared radio and X-ray measurements help reveal galaxies and clusters in this hidden zone. The Norma cluster is one important concentration, but the observed flow also reflects more distant structures, including the Shapley concentration. The Shapley concentration contains a dense assembly of galaxy clusters farther away. Its mass influences motions across a surrounding volume. Observations indicate that the movement of the local group cannot be explained by one nearby source alone. Instead, several overdense regions attract matter, while nearby underdense regions contribute by providing less gravitational resistance. The resulting velocity is a combined response to the uneven distribution of matter across the local cosmic web. Superclusters often appear impressive in galaxy maps, yet much of their volume remains nearly empty. Bright clusters occupy only small parts of the total region. Long filaments connect them, while broad spaces between the strands contain few galaxies. Dark matter forms the dominant gravitational framework. Hot gas fills cluster interiors, and thinner gas extends through the connecting network. Ordinary stars contribute only a small fraction of the total mass. The question of whether a supercluster is gravitationally bound requires careful definition. A bound system has enough gravity to resist cosmic expansion and remain together over very long periods. Individual clusters can be bound, as can many galaxy groups. Entire superclusters are usually too large and too diffuse for all their parts to collapse into one object. Accelerated expansion increases separation between distant components. Some central regions may remain connected, while outer parts gradually move beyond mutual influence. Astronomers estimate supercluster masses using several methods. Galaxy velocities reveal how strongly gravity acts within a region. X-ray observations measure hot gas in clusters. Gravitational lensing traces total mass, including dark matter. Counts of galaxies provide another estimate when calibrated against better measured systems. Each method has uncertainties because the structures are irregular, incomplete, and not always in equilibrium. Combining observations gives a more reliable picture than relying on one measurement alone. Large redshift surveys are especially important. They map millions of galaxies across broad areas of sky and reveal chains of clusters extending through space. Computer algorithms identify regions where galaxy density exceeds the average. Some methods use connected density thresholds, while others examine watershed patterns in velocity fields. The selected definition changes the number, size, and shape of identified superclusters. Scientists therefore compare catalogues carefully before drawing conclusions about their abundance. The distribution of superclusters tests models of cosmic structure formation. Simulations begin with small, early density variations and follow the motion of dark matter and gas through an expanding universe. Over time, dense regions become clusters and connected concentrations. The largest patterns depend on the amount of matter, the nature of dark energy, and the statistical properties of the initial variations. Observed supercluster sizes and frequencies broadly match the standard cosmological framework, although unusual individual structures require detailed analysis. Some reported structures appear to extend across more than 1 billion light-years. Their interpretation can be difficult because chance alignments survey boundaries and chosen linking rules may join separate concentrations into one named feature. A very long chain of galaxies does not necessarily form a coherent physical system. The important questions concern density, connectivity, velocity, and statistical significance. Current evidence supports very large patterns, but it also shows that the universe becomes nearly uniform when averaged across sufficiently great distances. Environmental effects continue within supercluster regions. Galaxies entering clusters may lose gas through interactions with hot plasma. Encounters can disturb disks and alter star formation. In lower density filaments and groups, these processes are gentler. A single supercluster therefore contains many environments, from crowded cluster cores to quiet bridges and sparse outskirts. Its broad identity does not erase the local conditions that govern individual galaxies. Seen across these distances, a supercluster resembles a continental region in the cosmic web. It contains many gravitational centers rather than one dominant core. Its shape is drawn by galaxy motions, dark matter concentrations, and connecting filaments. Some parts slowly gather while others separate with expansion. The supercluster remains a useful map of large-scale organization, showing how clusters and groups occupy shared valleys in the gravitational landscape without forming one unified object. Galaxy cluster domains are dense regions where hundreds or thousands of galaxies occupy a shared gravitational environment. A cluster extends across several million light-years and contains far more mass than visible galaxies alone can explain. Most of its mass is dark matter, while much of its ordinary matter exists as extremely hot gas between galaxies. Stars, planets, dust, and cold gas form only a smaller fraction. The cluster is therefore not simply a crowded collection of galaxies, but a vast system of matter in several forms. Gravity binds the central parts of many clusters strongly enough to resist cosmic expansion. Galaxies move through the cluster at speeds of hundreds to more than 1,000 kilometers per second. Their motions appear disordered because each follows a different orbit through the cluster's gravitational field. These velocities provide one way to estimate cluster mass. If only visible stars and gas were present, the observed speeds would often be too high for it to remain bound. The additional gravity is attributed mainly to dark matter. Dark matter forms an extended halo around the cluster. It is distributed more broadly than the central concentration of bright galaxies and hot gas. Its presence is measured through galaxy motions, gravitational lensing, and intra-cluster plasma behavior. Gravitational lensing occurs when the cluster's mass bends light from more distant galaxies. Strong lensing can produce bright arcs, distorted images, and several copies of one background source. Weak lensing creates smaller shape changes that become visible only after many background galaxies are analyzed together. The hot gas between galaxies is called the intra-cluster medium. It reaches temperatures of tens of millions of degrees Celsius, so it emits strongly in X-rays rather than visible light. This plasma contains hydrogen, helium, and traces of heavier elements produced by earlier generations of stars. Supernova explosions and stellar winds release these elements into surrounding space. Over time, galaxy motion and gas flows spread them throughout the cluster, creating a broad chemical record of past stellar activity. The intracluster medium is thin by earthly standards, yet its enormous volume gives it substantial mass. In many clusters, it contains more ordinary matter than all member galaxies combined. The gas remains hot because particles move rapidly and because matter falling into the cluster is compressed and shocked. Mergers between clusters can generate enormous shock fronts, turbulence, and regions of uneven temperature. These events unfold over hundreds of millions of years. Clusters grow by drawing in galaxies, groups, dark matter, and gas from surrounding filaments. Their development is gradual and uneven. Some appear relaxed, with a smooth distribution of X-ray gas and a dominant galaxy near the center. Others show signs of recent mergers, including separated gas clouds, disturbed galaxy patterns, and offsets between ordinary matter and dark matter. These differences reveal each cluster's present stage of assembly. At the center of many rich clusters lies a very large elliptical galaxy. It often contains hundreds of billions of stars and extends farther than ordinary galaxies. Its outer envelope can blend into diffuse intracluster light, a faint glow produced by stars no longer bound to any single galaxy. These stars may be removed during close encounters or cluster mergers. Their distribution provides evidence of the cluster's past interactions and the gradual disruption of smaller systems. The central galaxy frequently surrounds a massive black hole. Gas near the cluster center can lose energy through radiation and begin to move inward. Without a source of heat, some models predict that large amounts of gas should cool rapidly and form many new stars. Observations usually find less cooling and star formation than expected. Energy released by the central black hole appears to heat or disturb the gas, reducing the cooling rate. This process is called feedback, though its precise efficiency varies from cluster to cluster. Radio observations often reveal large bubbles and cavities in the hot gas. These structures form when jets from the central black hole push plasma outward. The cavities can rise through the surrounding medium and distribute energy across broad regions. Sound waves, weak shocks, and turbulence may also carry heat. This interaction helps regulate the cluster center linking activity near a black hole with gas extending across hundreds of thousands of light years. Galaxies change as they move through the cluster environment. A galaxy passing through hot intra-cluster gas experiences pressure that can remove its colder gas. This process is called ram pressure stripping. Without a continuing supply of cold material, star formation may decline. Close gravitational encounters can also disturb stars and gas, particularly when galaxies pass at high speed. Repeated, weaker interactions gradually alter shapes, remove material, and build the diffuse stellar population between galaxies. Clusters contain a mixture of galaxy types. Their dense central regions often have many elliptical and lenticular galaxies with older stars and little current star formation. Spiral galaxies are more common towards the outskirts where environmental effects are less intense. This pattern is not absolute and individual histories vary. Some galaxies enter as members of smaller groups and undergo changes before reaching the main cluster, a process sometimes called pre-processing. Astronomers study clusters at many wavelengths. Optical images show galaxies and gravitational arcs. X-ray telescopes trace hot gas. Radio instruments detect jets, relics, and diffuse emission linked to magnetic fields and energetic particles. Microwave observations measure the Sunyaev-Zeldovich effect, in which hot electrons slightly alter the energy of cosmic microwave background photons passing through the cluster. This signal helps identify clusters across great distances and estimate the pressure of their gas. Galaxy clusters are useful for testing cosmology because their abundance depends on how quickly structure grows. Massive clusters are rare, especially in the early universe. Counting them across different epochs constrains the amount of matter, the strength of density variations, and the expansion history. The measurements require careful mass estimates and well-understood selection methods. Despite these challenges, clusters remain among the clearest examples of gravity shaping matter on enormous scales. Within a cluster domain, galaxies occupy only small luminous points inside a much larger gravitational system. Dark matter defines the broad potential. Hot plasma fills the space between galaxies, and repeated infall slowly increases the total mass. The cluster becomes a crowded but ordered region held together by gravity and continually reshaped by motion, heating, stripping mergers, and the quiet circulation of matter. The outer boundaries of galaxy clusters form transition zones rather than sharp edges. In these regions, the central cluster gradually gives way to filaments, smaller groups, isolated galaxies, dark matter, and thin intergalactic gas. Matter still responds to the cluster's gravity, but not every object is bound. Some galaxies fall inward for the first time, some pass through and move outward again, and others remain beyond the cluster, while still sharing part of its surrounding gravitational environment. A cluster boundary can be defined in several ways because different forms of matter do not end at the same distance. The visible galaxy population becomes less concentrated outward while dark matter extends farther and hot gas fades into the lower density medium around the cluster. Astronomers often use a radius within which the average density is a chosen multiple of the cosmic critical density. This provides a useful measurement, but it does not create a physical wall. Matter motion and pressure continue beyond that radius. The infall region lies outside the settled central domain. Galaxies here move inward along filaments and sheets that connect the cluster to the cosmic web. Their velocities contain both the expansion of the universe and the local pull of the cluster. By measuring redshifts and estimating distances, astronomers reconstruct the pattern of infall. The result shows a region where gravity slows outward expansion and redirects motion toward the central concentration. Some galaxies reach a point where the cluster's gravity becomes strong enough to separate their motion from the surrounding cosmic expansion. This location is sometimes called the turnaround region. Inside it, matter is more likely to fall toward the cluster rather than continue moving away with the general expansion. The exact boundary is irregular because filaments groups and other mass concentrations alter the gravitational field. It also changes over time as the cluster grows. Farther inward, newly arriving material may cross a region where infalling gas is compressed and heated. Computer models predict an accretion shock around many massive clusters. The shock forms when cool intergalactic gas meets hotter, denser gas influenced by the cluster. Its position can be farther from the center than the bright X-ray region. Direct detection remains difficult because the gas is faint and the shock surface is uneven. Dark matter does not experience pressure shocks, but its particles change direction as they move through the cluster's gravitational potential. Simulations show a characteristic feature near the greatest distance reached by recently accreted dark matter after its first passage through the center. This feature is called the splashback radius. It marks a steep change in the dark matter density profile and can also influence the distribution of galaxies. Observations indicate evidence for such boundaries, although measured positions depend on cluster growth and selection methods. A galaxy near the splashback region may already have passed through the cluster once. During that passage, it can lose gas, experience tidal forces, and have its star formation reduced. When it later moves outward, it may appear beyond the usual cluster radius, even though its properties carry the effects of the inner environment. Such objects are often called backsplash galaxies. Their presence makes the outer boundary a record of orbital history rather than a simple division between processed and untouched systems. Many galaxies enter clusters as members of smaller groups. These groups can begin changing before they cross the main cluster boundary. Interactions between member galaxies, removal of loosely bound gas, and heating by the group environment may already reduce star formation. When the group falls inward, the cluster's tidal field can stretch and disrupt it. Some members separate onto different orbits, while the group's dark matter halo is gradually stripped. The gas surrounding an infalling galaxy feels pressure from the cluster medium. Even in the outskirts, this pressure can remove diffuse material from the galaxy's outer halo. The colder gas inside the disk may remain for longer, allowing star formation to continue temporarily. As the galaxy moves deeper, stronger pressure can strip denser gas and produce tails extending behind it. The outer boundary, therefore, contains galaxies at many stages of environmental change. Tidal forces also operate across the outskirts. The gravitational pull is stronger on the side of a galaxy or group facing the cluster than on the far side. This difference can remove stars and dark matter from weakly bound outer regions. The stripped material joins diffuse streams or the extended cluster halo. Because these processes occur slowly and at low surface brightness, much of their evidence is difficult to observe without deep imaging. The intracluster medium becomes thinner towards the edge, but it does not disappear abruptly. X-ray emission weakens because it depends strongly on gas density, making the outskirts difficult to measure. Microwave observations of pressure and absorption studies using background sources provide additional information. These measurements suggest that the outer gas can be clumpy, with denser clouds embedded in a more diffuse medium. Such clumping can bias estimates of gas density and temperature if it is not accounted for. Cluster outskirts are also locations where large-scale shocks and turbulence develop. Merging groups disturb the surrounding gas, while matter arriving along filaments produces uneven heating. Radio observations sometimes reveal broad relics near cluster edges. These faint structures trace energetic particles and magnetic fields associated with shocks. Their shapes and locations provide clues about past mergers, although the detailed process that accelerates the particles remains under study. Astronomers use the outer regions to measure how clusters assemble. The number and motion of infalling galaxies reveal current growth. The distribution of dark matter shows where recent material reaches the end of its first orbit. Gas temperature and pressure record accretion from the cosmic web. Because the outskirts are not fully relaxed, equilibrium-based mass estimates become less reliable there. Researchers therefore combine lensing galaxy dynamics, X-ray data, and microwave signals. At the outer boundary, a galaxy cluster merges gradually with its surroundings. No single line separates cluster space from intergalactic space. Instead, gravity, gas pressure, orbital history, and cosmic expansion define overlapping zones. Galaxies arrive along filaments, groups, break apart, gas heats in shocks, and dark matter settles through repeated passages. The outskirts preserve this continuing exchange, showing the cluster not as a finished object, but as a growing concentration whose influence extends far beyond its bright central region. Intergalactic gas reservoirs fill the spaces between galaxies with matter so thin that it is almost impossible to imagine on an earthly scale. Most of this material consists of hydrogen and helium left from the early universe, mixed with smaller amounts of heavier elements released by stars. The gas is not distributed evenly. It gathers along filaments, spreads through sheets, surrounds galaxy groups, and becomes extremely sparse inside cosmic voids. Although it emits little visible light, it contains a significant share of the ordinary matter in the universe. The simplest component is neutral hydrogen, in which electrons remain bound to protons. In low-density regions exposed to energetic radiation, much of the hydrogen becomes ionized, meaning that electrons separate from atomic nuclei. The balance between neutral and ionized gas depends on temperature density and the surrounding ultraviolet background. This background is produced mainly by galaxies and active galactic nuclei, whose radiation travels through intergalactic space and alters the state of the gas. Astronomers often detect intergalactic hydrogen through absorption rather than direct emission. Light from a distant quasar passes through clouds of gas before reaching a telescope. Hydrogen atoms remove light at specific wavelengths, leaving dark lines in the quasar spectrum. Because each cloud lies at a different distance, cosmic expansion shifts each absorption line by a different amount. The spectrum becomes a sequence known as the Lyman alpha forest, recording many separate regions of hydrogen along one line of sight. These absorption features range from weak lines produced by diffuse gas to strong systems associated with denser clouds. The weakest lines trace the broad intergalactic medium, while stronger absorbers may arise near galaxies within extended halos or in compact concentrations. By measuring line shapes, astronomers estimate temperature and motion. By comparing lines from hydrogen, helium, carbon, oxygen, and other elements, they study chemical composition and the history of enrichment. Most of the intergalactic medium is not neutral. It exists as plasma, a gas of charged particles. Its temperature varies widely. Some regions remain relatively cool at around 10,000 degrees Celsius, maintained by a balance between photoionization heating and expansion cooling. Other regions become much hotter as gravity draws matter into filaments and groups. Collisions and shocks convert large-scale motion into heat, producing gas at hundreds of thousands or millions of degrees Celsius. This warmer component is called the warm-hot intergalactic medium. It is important because observations of nearby stars and galaxies account for less ordinary matter than early universe measurements predict. Cosmological simulations indicate that much of the missing material is not absent, but spread through warm and hot filaments too faint for easy detection. Ultraviolet and X-ray absorption lines provide evidence for this reservoir, especially through highly ionized oxygen. The broad picture is supported, although the exact distribution remains uncertain. Direct emission from intergalactic gas is difficult to measure because the density is extremely low. Emission becomes weaker when particles rarely collide. Faint Ultraviolet X-ray and radio signals can still arise from denser regions, especially near filaments and galaxy groups. Sensitive instruments sometimes detect the signals by combining observations from many similar locations. Stacking increases the average signal while reducing random noise, allowing diffuse matter to emerge statistically, even when individual structures remain invisible. The gas carries heavier elements often called metals in astronomy, despite being far less abundant than hydrogen and helium. These elements originate inside stars and spread outward through supernova explosions, stellar winds, and outflows driven by black holes. Galaxies do not retain all the material they produce. Energetic events can push enriched gas beyond galactic disks and into surrounding halos. Over time, some of it enters intergalactic space and mixes with more primitive material. Metal enrichment is uneven. Gas near galaxies usually contains more heavy elements than gas far inside voids. Outflows travel along paths shaped by density and pressure, so they may enrich some directions more than others. Small galaxies can lose material more easily because their gravity is weaker, while massive galaxies and groups hold hotter, more extended atmospheres. Measurements of carbon, silicon, oxygen, and neon help reveal how far enriched gas travels and when it leaves galaxies. Intergalactic gas also exchanges matter with galaxies. Cool material can flow inward along filaments, supplying fuel for star formation. Hotter gas may enter a galaxy halo, remain suspended, then cool gradually before reaching the disk. At the same time, stellar feedback and black hole activity send gas outward. The boundary between a galaxy and the intergalactic medium is therefore active and permeable. Matter circulates through inflow, heating, cooling star formation and ejection. Magnetic fields thread parts of the intergalactic medium. Their strength is far weaker than typical fields inside galaxies, and their origin remains uncertain. Some may begin in the early universe, while other fields may be carried outward by galactic winds and active nuclei. Radio observations and the rotation of polarized signals provide indirect limits. Detecting these fields is difficult because the gas is thin and the expected effects are small. Fast radio bursts offer another method for studying diffuse matter. These brief radio pulses travel across great distances, and free electrons delay lower frequency waves slightly more than higher frequency waves. The total delay measures the number of electrons along the path. When the distance to the source is known, the signal helps estimate how much ionized matter lies between galaxies. Repeated measurements from many directions can map the distribution of otherwise invisible electrons. The pressure of intergalactic gas affects how structures grow. Cool gas falls more easily into small dark matter halos, while hot gas resists compression. Ultraviolet radiation can prevent gas from settling into the smallest halos, limiting star formation there. Shocks around filaments and groups raise entropy, a measure related to how widely heat is distributed. These processes influence which halos gather fuel and which remain dark. Across intergalactic space, gas exists in several overlapping states rather than one uniform phase. Some remains cool and photoionized, some becomes warm through gentle shocks, some reaches X-ray temperatures near clusters and groups, some forms denser clouds near galaxies. Together, these reservoirs connect the luminous parts of the universe. They store ancient hydrogen, receive elements from stars, carry matter into galaxies, and preserve the thermal history of cosmic structure. Though nearly invisible intergalactic gas forms a continuous material background through which galaxies evolve and exchange matter. Isolated galactic environments occupy regions where a galaxy stands far from clusters, massive groups, and dense filaments. Such isolation is never absolute, because gravity extends across all distances, and faint companions may remain. Even so, some galaxies experience far fewer encounters than systems in crowded regions. Their development is shaped mainly by internal processes, slow gas accretion, small satellites, and the surrounding dark matter halo. Astronomers identify isolated galaxies by examining the number, mass, and distance of surrounding systems. A galaxy may be called isolated when no massive companion lies within a radius and velocity range. Different surveys use different thresholds, so catalogues do not always contain the same objects. Deep observations can reveal faint dwarf companions that earlier images miss. Isolation is therefore a measured condition rather than an empty state. Many isolated galaxies are spirals with disks of stars and gas. Their spiral patterns can develop without a companion. Density, waves bars, gravitational instabilities, and gas motion through the disk can organize stars into arms. Some isolated spirals show forms suggesting long periods without strong disturbance. Others remain asymmetric because uneven gas accretion, internal activity, or minor satellite interactions can alter one side more than the other. An isolated galaxy exists inside a dark matter halo. The halo contains the system's mass and extends beyond the visible disk. Its gravity controls stars and gas at large radii. Smaller dark matter concentrations may orbit within it sometimes, carrying dwarf galaxies. Even when no luminous companion is visible, unseen substructure can influence streams, warp disks, and disturb outer stellar populations through gravitational passages. Cold gas is important in quiet environments. Without a hot cluster atmosphere, a galaxy does not experience strong ram pressure stripping. Its reservoir of hydrogen can remain intact for long periods, allowing star formation to continue gradually. Radio observations often reveal neutral hydrogen extending beyond the bright stellar disk. This gas may form warped layers, broad rings, or uneven clouds, preserving evidence of accretion and earlier interactions. Gas can arrive from the intergalactic medium along filaments. The flow is slow and difficult to observe directly. Some material enters the outer halo where it can be heated, mixed, and cooled. Other gas may remain cool as it moves inward. Absorption lines in distant background spectra reveal diffuse hydrogen and metals around isolated galaxies. These extended gaseous halos form a bridge between the galaxy and surrounding space. Star formation in isolated galaxies depends on how efficiently gas becomes dense and cold. Spiral arms and bars compress clouds, while supernova explosions stir the interstellar medium. Young stars heat and ionize gas, and stellar winds return energy and elements to the disk. These effects regulate new star formation. Because external disturbances are limited, changes often unfold steadily, although central bursts can occur when gas moves inward. Bars are common in isolated disk galaxies. A bar is an elongated concentration of stars crossing the central region. It redistributes angular momentum and can guide gas toward the center. This inflow may support star formation or feed a central black hole. The bar can also create rings and organize spiral structure. Its growth and weakening reflect interactions among the stellar disk gas and dark matter halo. Central black holes in isolated galaxies can become active without a major merger. Gas clouds, stellar mass loss, internal instabilities, and small satellites can supply material. When matter falls toward the black hole, it heats and emits radiation. Most isolated galaxies are not active at any given time, but low-level activity is common. Dramatic collisions are therefore not required for every episode of black hole growth. Dwarf galaxies are found in isolated regions. Some contain abundant gas and form stars slowly, while others are faint and diffuse. Their weak gravity makes them sensitive to stellar feedback. Supernova explosions can push gas outward, temporarily reducing star formation. If the gas remains bound, it may cool and return. Their composition often reflects gradual enrichment with heavy elements accumulating slowly. Extremely isolated dwarfs provide tests of galaxy formation in low-density surroundings. They may retain primitive gas irregular shapes and extended hydrogen clouds, yet no galaxy remains unchanged since the early universe. Even quiet systems contain several stellar generations and traces of internal recycling. Claims that a nearby dwarf is truly young require caution because old stars can be faint beneath brighter, recent populations. Elliptical galaxies can also exist in isolation. Some may be remnants of mergers that occurred within small groups whose members eventually combined into one system. A bright, elliptical surrounded by extended X-ray gas and few comparable neighbors is sometimes associated with a fossil group. The remaining galaxy preserves evidence that the present quiet environment may follow an earlier period of strong interaction. Isolation can change over cosmic time. Galaxies move through the large-scale gravitational field, and small groups can disperse or merge. A galaxy now far from massive neighbors may have experienced encounters billions of years earlier. Astronomers search for tidal streams, shells disturbed outer disks, and unusual stellar motions to reconstruct this history. These faint structures can remain visible after the companion responsible has dissolved or merged. The stellar populations of isolated galaxies record a balance between calm growth and occasional disturbance. Older stars form broad disks, central bulges and extended halos. Younger stars trace gas-rich arms rings and irregular patches. Chemical abundances reveal how material circulates through successive generations. Differences between central and outer regions show how disks build over time, often with younger populations farther from the center. Because isolated galaxies lack strong environmental pressure, they provide a reference for comparison with cluster and group systems. Their gas content, star formation shapes, and black hole activity help separate internal evolution from externally driven change. They show that galaxies can transform through bars, feedback accretion, and minor mergers, even in quiet surroundings. Their apparent solitude is not inactivity, but slower exchange within extended halos. Across these sparse regions, the space between large galaxies may span millions of light years. Only faint dwarfs, thin gas, and dark matter interrupt the distance. The isolated galaxy continues to rotate, form stars, recycle elements, and gather material at a measured pace. Its structure reflects present, calm, and hidden history. In this environment, galactic evolution proceeds without constant pressure from a crowded domain, revealing the quiet processes that shape a system from within. The local cosmic volume is the nearby region of the universe where individual galaxies can be mapped with unusual detail. It extends across tens of millions of light years around the Milky Way and contains galaxy groups, short filaments, thin sheets, and broad underdense spaces. On this scale, the cosmic web is no longer seen only as a statistical pattern. Its separate parts can be traced through direct distance measurements, galaxy motions, neutral hydrogen surveys, and deep images of faint systems. The distribution is uneven. Galaxies gather into small groups and loose associations rather than forming one continuous concentration. Between these gatherings lie quiet regions with very few luminous systems. Some galaxies sit along narrow strands that guide their motion toward denser areas. Others occupy flattened structures where many nearby systems share similar positions and velocities. These local features are modest compared with the largest cosmic walls, yet they follow the same gravitational pattern established across the wider universe. One important structure is the local sheet, a flattened arrangement of nearby galaxies extending for several million light years. The Milky Way lies within this sheet along with many neighboring systems. Their positions form a relatively thin layer compared with its width. The sheet is not a solid plane and its boundaries are gradual. It represents a region where matter has collected into a flattened configuration under gravity, while nearby underdense regions expand more freely. Galaxies in the local sheet share part of a broad motion through space. This motion does not mean that every galaxy travels in the same direction at the same speed. Each also responds to nearby groups and its own companions. When these smaller motions are averaged, a coherent flow appears. Astronomers reconstruct it by comparing a galaxy's measured redshift with an independent estimate of distance. The difference reveals a peculiar velocity, which is motion beyond the general expansion of the universe. Accurate distances are essential in the local cosmic volume. Redshift alone becomes less reliable nearby because peculiar velocities can represent a significant part of the measured motion. Astronomers therefore use stars and stellar events whose brightness can be related to distance. Cepheid, variable stars change brightness in a regular pattern connected to their true luminosity. The brightest red giant stars also provide a useful distance indicator. In some galaxies, supernovae extend the scale to greater distances. These methods create a three-dimensional map of nearby space. Each galaxy receives a position across the sky and a distance along the line of sight. When many measurements are combined, sheets, groups, filaments, and voids emerge. The map is incomplete because faint, dwarf galaxies remain difficult to find, especially behind the bright stars and dust of the Milky Way. Radio surveys help by detecting neutral hydrogen even when visible light is obscured. Dwarf galaxies dominate the number of known systems in the local cosmic volume, although large galaxies dominate its light and stellar mass. Many dwarfs are irregular, diffuse, or extremely faint. Some contain enough gas to continue forming stars, while others contain mostly older populations. Their visibility depends strongly on surface brightness. A galaxy can contain many stars yet remain difficult to detect if they are spread across a broad area. Deep surveys repeatedly discover new dwarfs around nearby groups and in quieter regions. These findings test models of dark matter because simulations predict large numbers of small halos. Not every halo necessarily forms a visible galaxy. Gas may fail to cool, ultraviolet radiation may suppress star formation, and stellar feedback may remove material from shallow gravitational wells. The comparison between predicted halos and observed dwarfs remains an important area of research. The local void forms a major underdense region beside the local sheet. It contains far fewer galaxies than average and occupies a large nearby volume. Its low density affects local motion because matter receives less gravitational pull from the void's direction and stronger pull from denser structures elsewhere. In practical terms, galaxies near its boundary move away from the underdense region relative to the surrounding cosmic frame. The void does not push them through a separate force. The motion arises from the uneven gravitational field. Other smaller voids and sparse zones break up the local map. Their boundaries are traced by strings of galaxies and loose groups. These underdense spaces continue to expand and become emptier relative to the average density. Small galaxies can still exist inside them, often following delicate internal filaments. Their isolation makes them useful for studying slow evolution in environments with few interactions. Nearby groups vary in size and structure. Some contain one dominant spiral or elliptical galaxy surrounded by dwarfs. Others contain several large members of comparable mass. Their galaxies may be gravitationally bound, but the groups are often not fully relaxed. Gas dark matter and satellites continue to move through them. Interactions can produce tidal streams, warped disks, and diffuse stars between galaxies. Because these systems are near, such faint features can be studied in greater detail than similar structures far away. The local region also contains the Virgo cluster, a large concentration positioned tens of millions of light-years from the Milky Way. Its gravity influences the motions of galaxies across a broad surrounding area. The cluster is not the sole cause of local flows because the local void nearby groups and more distant mass concentrations all contribute. Measurements show a complex velocity field shaped by several overlapping gravitational influences. Astronomers use the local cosmic volume as a laboratory for galaxy formation. Individual stars can be resolved in many nearby galaxies, allowing ages, chemical abundances, and star formation histories to be measured directly. Gas clouds can be mapped, satellite populations counted, and faint stellar streams followed. These observations connect small internal processes with the larger arrangement of the cosmic web. Across this nearby volume, the universe appears both structured and open. Galaxies gather in modest groups, align within sheets, and trace short filaments around dark spaces. Their motions reveal the pull of visible and invisible matter. Precise distance measurements turn the surrounding sky into a three-dimensional landscape. The local cosmic volume therefore provides the clearest nearby example of how gravity expansion, dark matter gas, and galaxy evolution combine within the broader architecture of space. Its close structures reveal cosmic organization where separate galaxies and their surrounding environments can still be examined clearly. The local group is a small collection of galaxies bound together by gravity within the nearby cosmic web. It spans roughly 10 million light-years and contains more than 100 known members, although the exact count changes as faint dwarf galaxies are discovered or reclassified. Most of its visible mass is concentrated in three large spiral galaxies: the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Around them move many smaller systems, including dwarf irregular galaxies, dwarf spheroidal galaxies, and a few compact companions. The local group does not form a smooth sphere. Its galaxies are distributed unevenly around the two dominant spirals. The Milky Way and Andromeda each possess their own families of satellite galaxies, while Triangulum occupies a smaller but significant position. Some dwarfs lie far from all three and may follow more independent paths. The outer boundary remains gradual because gravity does not stop at a fixed surface. Astronomers estimate membership by combining distance, velocity, and orbital information. The Milky Way and Andromeda contain most of the local group's stellar mass. Each has a rotating disk, a central bulge, an extended stellar halo, and a much larger dark matter halo. Their dark halos overlap the wider gravitational environment of the group. Triangulum is less massive, yet it contains an active disk with abundant gas and star formation. Its motion suggests a long association with Andromeda, though the exact history of their past encounters remains uncertain. Dwarf galaxies are the most numerous members. Many contain only a small fraction of the stars found in the Milky Way. Dwarf spheroidal galaxies have little gas and mostly old stars. They are faint, diffuse, and strongly influenced by dark matter. Dwarf irregular galaxies often retain neutral hydrogen and continue forming stars in scattered regions. Their uneven shapes reflect weak gravity, internal feedback, and occasional interactions with larger neighbors. The satellite population provides an important test of dark matter models. Simulations predict many small dark matter halos around galaxies like the Milky Way and Andromeda. Only some of these halos contain visible stars. The smallest halos may lose gas during the early ionization of the universe or through repeated stellar explosions. Others may never gather enough dense material to begin sustained star formation. Deep surveys continue to reveal extremely faint satellites, narrowing the difference between predicted and observed numbers. The plains formed by some satellite galaxies have attracted attention. Several Milky Way satellites appear aligned within a broad, flattened arrangement, and a similar pattern is observed around Andromeda. Some members may also share related directions of motion. It remains uncertain whether these structures are long-lived temporary or partly shaped by observational selection. Current simulations can produce flattened satellite distributions, but the frequency and stability of the observed patterns continue to be studied. Streams of stars cross the halos of the large galaxies. These streams form when a dwarf galaxy or star cluster is stretched by tidal forces. Stars are gradually removed and spread along the object's orbit, creating narrow arcs that can extend for tens of thousands of light years. Their shapes trace the gravitational field, including the distribution of dark matter. They also preserve evidence of past accretion, showing how large galaxies grow by absorbing smaller systems. The Magellanic Clouds are two prominent satellites of the Milky Way. Both contain gas-young stars and active star-forming regions. Their mutual interaction and their motion through the Milky Way's halo produce streams of hydrogen extending across the sky. The Large Magellanic Cloud is massive enough to disturb the Milky Way's disk and inner halo. Its first close passage may be recent on cosmic timescales, although orbital models depend on the mass of the Milky Way. Andromeda is surrounded by many satellites as well. Its large companion galaxies include Messier 32 and Messier 110, both of which show signs of interaction. Faint streams and shells around Andromeda reveal earlier mergers with smaller galaxies. Its stellar halo is more extended and disturbed than a simple, smooth model would suggest. These features indicate a long history of accretion and gravitational encounters within the local group. The space between the major galaxies is not empty. It contains thin ionized gas, dark matter-stripped material, and possibly clouds too faint to detect easily. Some gas may move between halos or remain in the broader group medium. Unlike a rich galaxy cluster, the local group does not contain a dense, bright reservoir of X-ray emitting plasma across its full volume. Its intergalactic medium is cooler and more diffuse, making direct measurement difficult. The group's total mass is estimated from galaxy motions. The approach of Andromeda towards the Milky Way provides one important constraint. Their mutual gravity has slowed the separation that would otherwise follow cosmic expansion and has drawn them into a bound orbit. Motions of distant dwarf galaxies provide additional information. Estimates vary because the dark matter distribution is extended and because only a limited number of tracers have accurately measured velocities. The local group is separated from neighboring groups by millions of light-years of relatively sparse space. The nearest comparable concentrations include the groups around Centaurus A, A1, and other nearby large galaxies. These systems belong to the same broader local cosmic environment but are not generally considered bound members of the local group. Their gravity still contributes weakly to long-term motion across the surrounding volume. Within the local group, timescales are immense. A dwarf galaxy can take billions of years to complete an orbit around a large spiral. Tidal stripping proceeds gradually, and gas loss may occur over several passages. Star formation rises and falls as gas is compressed, heated, or removed. The group changes continuously, but its structure remains recognizable across long periods because gravity keeps its main members associated. The local group is therefore both a neighborhood and a gravitational system. Its large spirals dominate the mass, its dwarfs preserve records of fragile galaxy formation, and its streams reveal ongoing assembly. Dark matter binds the whole region, while thin gas and scattered stars occupy the spaces between galaxies. Across this modest cosmic domain, the processes of orbit accretion, stripping, and star formation can be examined with unusual detail, making the local group the clearest nearby example of a small galaxy association shaped by gravity over billions of years within nearby intergalactic space. The expanse between the Milky Way and the Andromeda Galaxy stretches across about 2.5 million light-years. It separates two immense spiral systems whose halos extend far beyond their visible disks. From either galaxy, the other appears as a faint patch of light, yet the intervening space within the local group contains more than darkness. It holds thin gas, dark matter, scattered stars, small galaxies, and the slow influence of gravity acting across a span that light requires millions of years to cross. The visible disks occupy only a small fraction of this separation. The Milky Way's bright stellar disk extends roughly 100,000 light-years across, while Andromeda's disk is larger. Beyond each disk lies a stellar halo containing old stars, globular clusters, streams, and the remains of disrupted satellites. Dark matter halos reach hundreds of thousands of light years. Their exact boundaries are difficult to define because density falls gradually rather than ending at a sharp surface. Between the two great halos lies the broader medium of the local group. This region is extremely diffuse. Individual atoms can be separated by large distances, and most material produces almost no visible light. Some gas remains ionized by radiation from galaxies and the cosmic ultraviolet background. Other material may exist in cooler clouds or warmer filaments. Observations indicate that a substantial amount of ordinary matter associated with galaxy groups can be hidden in such extended gas, but the amount and distribution between the Milky Way and Andromeda remain uncertain. Dark matter supplies most of the mass governing the separation. It forms extended halos around both galaxies and contributes to the gravitational field of the local group. Dark matter does not create a luminous bridge that can be photographed directly. Its distribution is inferred from the motions of galaxies, satellite systems, stellar streams, and gas. Models suggest that the outer halos may approach or partly overlap within the group environment, although any boundary between them is gradual and dependent on definition. Small galaxies occupy parts of the expanse. Some are satellites of the Milky Way, others are associated with Andromeda, and a few lie far enough from both to have more independent histories. Dwarf galaxies are faint and often contain only a small stellar population. Their motions help trace the group's gravitational field. Their gas content and star formation histories also record whether they have passed near a larger galaxy or remained in quieter regions for much of their existence. The Triangulum Galaxy lies off the direct line between the two dominant spirals at a distance of several 100,000 light-years from Andromeda. Its presence makes the local group a three-body environment rather than a simple pair. Even so, the Milky Way and Andromeda dominate the total mass. Their mutual attraction shapes the motion of nearby dwarfs and influences how the surrounding dark matter and gas are distributed. Andromeda's light reaches the Milky Way after traveling for roughly 2.5 million years. The galaxy is therefore observed as it existed long before modern humans appear. Any change occurring there today will not be visible from Earth until the same travel time has passed. In the opposite direction, light leaving the Milky Way now will require a similar interval to reach Andromeda. The separation is not only spatial but also a delay in information, so each galaxy receives an ancient image of the other. Stars crossing the full distance would require enormous time, even at high speed. A star moving at 1,000 kilometers per second would still take hundreds of millions of years to travel from one major galaxy to the other. Most stars remain gravitationally bound to their original systems, and only rare objects may be ejected into intergalactic space. Some stars can become unbound through interactions with massive black holes. supernova explosions in binary systems, or complex gravitational encounters. Their journeys remain long and isolated. A few candidate stars have been observed far from obvious galactic disks, but determining their origins is difficult. Some belong to extended halos rather than truly intergalactic space. Others may form in faint tidal debris or be stripped from dwarf galaxies. Their chemical composition and motion can provide clues. An intergalactic star still emits light and evolves normally, but the sky around it would contain few nearby stars, with the Milky Way and Andromeda appearing as distant luminous islands. Gas clouds and tidal debris also move through the region. Past interactions among galaxies can remove stars and hydrogen, leaving streams that extend across large distances. The Magellanic Stream surrounds the Milky Way, while Andromeda has its own system of stellar and gaseous remnants. These structures do not span the entire gap as a continuous bridge, but they show that galactic boundaries are permeable. Material can leave one system orbit within the local group or join another halo over immense periods. The relative motion of Andromeda is measured through the shift of its light and the careful tracking of its position. Its overall motion toward the Milky Way produces a blue shift, meaning that observed wavelengths are compressed rather than stretched. The sideways component is much harder to measure because the apparent change across the sky is extremely small. Improved observations refine this motion, but uncertainties in velocity and total mass still affect calculations of the pair's long-term paths. Gravity acts continuously across the gap, yet the process is slow because the separation is vast. The two galaxies do not fall together as rigid objects. Their dark halos, satellite populations, disks, and surrounding gas all respond over different timescales. Nearby galaxies also alter the gravitational system. The space between the Milky Way and Andromeda therefore behaves as a broad, changing landscape rather than an empty corridor connecting two fixed points. Across this local gulf, light carries old images, gravity guides slow motion, and thin matter occupies the darkness between bright structures. The distance gives the local group much of its scale. It separates two dominant galaxies while still allowing them to remain gravitationally related. Within the expanse, dwarf galaxies move diffuse gas drifts, dark matter shapes, orbits, and rare stars travel through regions where luminous neighbors are absent. The space remains quiet, broad, and physically connected, an intergalactic domain measured not by emptiness alone, but by the slow exchange of influence across millions of light years. The edge of the Milky Way is not a single line where the galaxy suddenly ends. It is a broad transition, extending far beyond the bright disk, through faint stars, globular clusters, dark matter, and thin gas. The visible spiral pattern occupies only the inner part of this larger system. Beyond the familiar bands of stars, the galaxy becomes increasingly diffuse, until its material blends into the surrounding environment of the local group. The stellar disk reaches roughly 100,000 light-years across, though its exact diameter depends on which stars and gas are included. Its outer regions contain fewer stars, lower gas density, and weaker star formation. Neutral hydrogen extends beyond much of the stellar light, forming a thin, uneven layer shaped by gravity, satellite interactions, and the pressure of surrounding gas. Past the disk lies the stellar halo, a vast, nearly spherical region containing old stars and globular clusters. Its stars are spread so thinly that the halo contributes little visible brightness compared with the disk. Many halo stars move on tilted or elongated paths rather than following the organized rotation of the spiral arms. Their motions and chemical compositions reveal several origins, including early star formation and the gradual absorption of smaller galaxies. Streams of stars cross the halo like faint arcs. They form when a dwarf galaxy or globular cluster is stretched by the Milky Way's gravity. Over repeated orbits, stars leave the smaller system and spread along its path. Their shapes trace the gravitational field and help reveal how mass is distributed far from the galactic center. The stellar halo does not have a simple outer boundary. Isolated Milky Way stars can be found hundreds of thousands of light-years from the disk. Some are bound on distant orbits, while others may be escaping. A star near the edge can move slowly relative to the galaxy, yet still remain connected by gravity across an enormous orbit lasting billions of years. Beyond most halo stars lies the circumgalactic medium, a reservoir of gas surrounding the Milky Way. This gas extends far outside the disk and contains several temperature phases. Some clouds remain cool enough to contain neutral hydrogen. Other regions are warm and ionized, while a larger volume may consist of hot plasma at temperatures of millions of degrees Celsius. The gas is difficult to image directly because it is thin and faint. Astronomers detect much of this medium through absorption lines. Light from distant quasars passes through the Milky Way's extended gas before reaching telescopes. Atoms and ions remove light at specific wavelengths, revealing hydrogen, oxygen, carbon, silicon, and other elements. These measurements show that the outer gas is chemically enriched, meaning that some of it has been processed inside stars and later expelled from the disk. The circumgalactic medium acts as a reservoir and exchange zone. Gas can move inward, cool, and eventually help form new stars. At the same time, supernova explosions, stellar winds, and activity near the central black hole can push material outward. Some outflowing gas remains bound and later returns, creating a slow circulation. High-velocity clouds occupy parts of the outer halo. Their motion differs strongly from the rotation of the disk. Some may be in falling materials, some may be debris from satellite galaxies, and some may belong to large structures such as the Magellanic Stream. Their distances are often difficult to determine, making their total masses uncertain. Even so, they provide direct evidence that the outer galaxy contains moving gas rather than empty space. The Magellanic Stream is one of the largest gaseous structures around the Milky Way. It is associated with the Large and Small Magellanic Clouds and extends across a portion of the sky. Gravity, gas pressure, and interactions between the clouds help remove material from them. Parts of the stream may eventually fall toward the Milky Way, while other parts may disperse into the surrounding halo. Dark matter dominates the galaxy's outer mass. Its halo extends far beyond the visible stars and gas, perhaps reaching several 100,000 light-years or more. The density declines gradually with distance, so any chosen edge depends on definition. One boundary may describe where matter has completed an orbit around the galaxy. Another may mark where the Milky Way's gravity becomes comparable to the influence of Andromeda and the wider local group. The outer dark matter halo is inferred through the motions of satellite galaxies, globular clusters, stellar streams, and distant halo stars. Estimates of the Milky Way's total mass therefore vary. The largest uncertainty comes from the outermost distances where few traces exist and where the gravitational influence of neighboring systems becomes more important. Small satellite galaxies move